Hello everyone, this is Group G. We are going to present this paper. I will go an overview of what this paper is about. This is called Practical Application Focused Online VI Curve Monitoring System for Power Semiconductor Devices. This is by Mr. Bayer Khan and Omora. This is the abstract. This is the introduction of the paper, and then we have here the comparison of preventive maintenance strategies for power semiconductor devices, and then part 2, this is the monitoring system configuration and design. This is the components. This is the components for the proposed real-time VI curve monitoring system integration. This is also another diagram that shows the sinusoidal current for the normally operating full bridge inverter. As you can see here, there is a full bridge inverter, and then we have here more components in this fishbone pattern, in this external noise shield. And then we have here the comparison for current measurement, another image. And then here we have the signal waveforms and their timing relation for ADC, analog digital converter sampling operation. And then here we have the results of the monitoring. This is the schematic test setup for A, this part here. This is the full bridge inverter circuit. And then the B and the C is voltage and current measurement circuit. And then D is the complete monitoring system. This is the SD card and the MCU. This is the table that shows the specifications for the full bridge inverter, and this is the experimental setup if you would like to set up the whole system. And then we have this is the online VI curve monitoring for verification. This is another graph to show the real-time acquisition of on-state voltage. And then here we have the comparison for curve tracer measurement, and then another graph here and another graph here for the real-time acquisition. And then we have this other curve. This is for the monitored VI curve. We have this graph as well. This is the 3D lookup on the X, Y, and Z axis to show the monitoring system. And then last, we have this multivariate t-square outlier-based approach. This is the example of the 3D data points transformed in this space. Another graph to show the residual voltage at different case temperatures. And then this is another graph for the distribution of the hoteling. These are more graphs. And then we have the limitations. And this part is the conclusion. So we would present this in our PowerPoint in this following presentation. So,
Okay, guys. I'm gonna take over. So, our PPT name is Online V Until One Curve Monitoring System for Power Semiconductor Device from Group G. That's presented by me, Akrom, Ferdian, Junola, Omari, Yanka, Shannon, Aurelia, and Aqila Wicaksono. Okay, introducing the problem. The problem that we currently have is power electrons are critical in EVs, photovoltaics, and industrial drives. Device failure equals downtime and expensive replacement and need early degradation detection. And the message that we want to send out is why monitoring device matter in semiconductor. Motivating an object, the motivation of and the objective of the V until one monitor is the motivation is failure causes downtime and expensive module replacement. Manufacturer need a method to take a listen of degrees, not only final failures. Traditional monitoring is offline and cannot detect real-time performance changes. And the objective is develop an online system to capture V and one curves spontaneously, create a baseline signature from healthy device operation, and build statistical or ML-based detection of abnormal behavior. What is a V under one curve? V under one curve is a graph that shows how much current flows to the device when different voltages are applied across it. When voltages are applied across it, it reveals the electrical behavior of a semiconductor, showing when it starts conducting, how strongly it conducts, and how it reacts under different conditions. Okay, so you guys can see the image right on the like left, yeah. But that's basically how a V under one curve works. Like there's a current flow, and then there's a like a forward curve and a reverse voltage and all of that. Next. Okay. The type of power in semiconductor device, there's three. Number one is MOSFET, or commonly known as metal oxide semiconductor field effect transistor, that is used in high-speed switching application, and the key parameter is RDS on, and degradation often increases conduction loss. The second one is IGBT, or insulated gate bipolar transistor, handles high power and high current, common in inverters and motor drives. The grading usually caused uh by thermal cycle and one wire. And the third one is Ferdian, pro- provides undirectional current flow. And secondly is degradation appears as for voltage increase or higher leakage and simple structure but critical in converters. Yes. Okay, there's so basically it's just like the image is clean from the slide before, like MOSFET, you can see there's three pin G, D, and S, and then also like N channel and P channel MOSFET. MOSFET is used for fast switching, low voltage application. Watch for RDS increase. We already explained that in the slide before. And then there's IGBT, like there's three pin, and then you could see like there's a transistor like there. And then IGBT is a high power switching aging seen as higher PCE. And the last one is power diode. So the image explain there's in the power diode there's two opposites, like there's cathode and there's anode. And then fast diode and power diode symbol device degradation shown by 4 voltage switch. Mm. Okay, system architecture overview. Number one is hardware component. Voltage sensor captures real-time voltage across devices. Current sensor measures device current, and high-speed ADC digitize the analog signal. Software signal processing, filtering noise, removal low pass or smoothing, normalization temperature, and supply consumption. And also real-time V under one curve extraction. The last one is data collection monitoring interface. PC dashboard or GUI for visualization, SCADA or cloud platform for logging, and alert system for like threshold and anomaly scores. Okay, so we have an electronic block diagram here. The electronic block diagram illustrates the complete flow of data in the VLDO monitor. It shows how electrical signal move from the semiconductor device through sensing and processing stages. Under there is the monitoring interface. Each block represents a key function in the measurement analysis point. Okay, so basically, if you look at the image, you just tell us how the data flow from the beginning until to the end in the VLDO monitoring system.
And now the measurement and methodology of our of the power monitoring system. Uh, the first method is signal acquisition. So the voltage and current of a system that's being monitored is measured simultaneously, and high-speed sampling is required to capture the shape of the VI curve. Um, this way, the system ensures synchronization between voltage and current so that we don't have any mismatched values within the VI curve. Next, we perform filtering and noise reduction. Uh, raw, which include raw measurements, include noise from switching devices, electromagnetic interference or EMI, and just the surrounding environment is just called noise. And so to reduce this noise and filter it, we apply low pass filters, moving average, or a Savitsky-Goulet filter. So the reason we do filtering is to just produce clean, smooth VI curves without any spikes or drops. And next we have normalization and compensation. VI curves depend on temperatures, supply voltage, and load variations for it to be graphed. And normalization helps and compensates for these variations, so only the true degradation is seen. Next, uh, the next method we have is VI curve reconstruction, which we take the sampled voltage and current points, and then we plot them onto a continuous curve. And curve reconstruction converts this discrete data into a readable signature with with continuous graphs. And then we have feature extraction, which we extract key features from the curve, like the forward voltage, the slope or dynamic resistance, and the leakage curve. And then next we have data logging, which just means we log each measurement of voltage and current to a set timestamp, to a set temperature, and to a set device ID, so that we don't confuse the conditions between other devices or other conditions that we need to test, we need to monitor. Next. Here we have the flow chart for the measurement methodology. So first off, we take the raw signals, we measure them, and we clean them, transform them in filtering, and after we filter them, we take the data points and plot them onto the curve uh, in curve reconstruction. After we have successfully reconstructed the curve, we extract the features of the curve itself and the other um, aspects. And then after all of that, we log all the data, including the extracted features with the set conditions that we have already determined before the monitoring. Next. So in order for us to test whether or not the uh, monitor system works, we need to have an experimental setup. So the test environment and conditions used in the paper itself in the monitoring system um, needs to be used in a controlled temperature environment with a controlled load and controlled operating cycles, controlled frequency and period amplitude. Um, so repeat stress cycles like cycles that involve like high amplitudes and high frequencies will cause the device to experience degradation, real world degradation. So we can add that the system records thousands of VI curves across different conditions to build a reliable data set, uh, so that we can compare which conditions degrade the device more or not. After we set up the test environment and conditions, we use instrumentation. So we set up the power supply, the load bank, the temperature chamber sensors, and data acquisition devices like voltmeters, ammeters, and what else? And all the instruments, measurement devices are to be standardized and recorded and synchronized with the time step that we have already determined. Next. Next. So the normal operation VI signature, there is an expected curve behavior for each device. So a healthy semiconductor will have a stable VI curve with minimal variation between cycles, like without noise, without any sort of transient signals out there. So the forward voltage and slope remain consistent, indicating normal consumption behavior. And because there is an expected curve, expected curve behavior, there's also a reference baseline curve. So the system initially establishes a baseline signature from the early stages of operation from t equal to 0. And we use that baseline curve at the start of the device's operation when it's essentially brand new to compare it with future curves, uh, with future curves of the device so that we can detect any deviation or any degradation within the device itself uh, in the future. And we need to reference it. And so we see the normal operation of the I signature, V1 signature, and we see that it shows a stable, predictable system behavior with a smooth curve and gradual rises, so that the peak plateaus at a certain point. So you see the V1 signature uh, starts at 0 at t equals 0, and as time goes on, the voltage increases exponentially and then logarithmically, and then it plateaus. Uh, so we can use that peak as a reference to as like the forward voltage, or so that we know in the future whether or not it is higher or lower than the measured voltage that we got from the baseline voltage. Next. Next, we have degradation indicators. There are plenty of them. The first of note is electrical shifts. So, like degradation in semiconductor devices often manifests in an increase in forward voltage, or changes in the slope of the VI curve, like it could be more negative or it could be more positive, and it could also a shift in terms of a rising leakage current. These electrical charges usually appear for the device completely breaks down, complete device failure. serving as early warning signs of wear or aging. And the next degradation indicator is curve instability and noise. As devices degrade, the VI curves may show more cycle-to-cycle variation, with more transient signals and more noise are present, with like irregular curve responses or hysteresis. And these fluctuations usually indicate that the device is unstable and there are signal developing faults within the device. Next. Next. So we see here the VI curve and in comparison with the normal and degraded. Here we see the blue line is the normal VI curve and the red dashed line is the degraded uh, semiconductor device curve. So we see that there is a slight slope change within the red curve as compared to the blue curve. And then there's the presence of hysteresis. Since the current depends on past voltage history, um, it, the presence of hysteresis is often caused by like a charge that's trapped in the semiconductor itself or other thermal effects. And there's also the presence of noise, which in healthy conditions usually don't appear, but if it's degraded, uh, the device will tend to catch that noise, and there will be random fluctuations or spikes in its degraded curve that suggests instability or intermittent connections. Next. Shannon.
Okay, so this is the fault detection algorithm. For the statistical analysis, the incoming VI curves are compared to baseline measurements using statistical tools. Deviations, threshold crossings, or anomaly scores are used to detect early signs of degradation, helping to identify potential faults before they escalate. And then feature-based classification. Specific features of the VI curve, such as slope, knee points, or leakage currents, are analyzed to classify the type of degradation. Both machine learning and rule-based methods can be applied to recognize particular failure modes. Then the fault detection process flowchart from VI curves to alerts. This flowchart describes the 4 key steps in the automated fault detection using the VI curves. First is the raw VI curve, and then the feature extraction, and then classification, and then the detection alert. This is the fault detection process flowchart. So the raw VI curve, that is the data collection of the components' electrical behavior. And then the feature extraction is calculating key health indicators like the slope, the hysteresis size, noise level from the raw curves. And then the classification is using algorithms like machine learning to label the components' state, such as normal or degraded, in a linear regression model. And then the fault detection alert notifies operators when a degradation state is identified, So if it's degradation, then it will alert the system. So this ensures that the proactive maintenance and system is reliable. Now we have the degradation of a MOSFET. There are three aspects to this. First is the real-time RDS tracking, which demonstrates an increase in on-state resistance over accelerated aging cycles, and then VI slope flattening, which shows how the degradation is visually captured by the flattening of the VI curve slope in the linear region. And then the early alert trigger indicates the specific cycle count, the null point of return, where the fault detection algorithm would have successfully issued an early alert before catastrophic failure. And then this is again the graph that shows the degradation of a MOSFET. The main plot, or the time series, this tracks the calculated on-state resistance against the number of operating cycles. The graph shows a steady increase due to aging, such as the bond wire liftoff. A critical alert threshold here is marked, and this shows where our point in the system would have issued an alert before it says the device has a failure. And then the inset VI curve comparison compares a healthy curve with the alert triggered curve. As you can see, the alert triggered curve is the red line and the healthy one is the blue line. The flattening of the slope down here on the degraded curve is a direct visual representation of the increased confirmation of the feature extraction's success. So here's the validation and performance metrics used in the paper. It's divided into three parts. The first is detection accuracy, second is system latency, and the third is false positive management. So in the detection accuracy, it presents the measured classification accuracy. For example, 98.5% of the system in distinguished normal from the degradation states. For the system latency, it details the real-time processing speed. For example, the alert is issued within 500 milliseconds of curve capture, and this emphasizes the ability to monitor high-frequency switching. And then the false positive management highlights the low false positive rates in which there is a false positive, which builds operator trust and prevents unnecessary maintenance shutdowns. And here's the conclusion and future work from the paper itself. Firstly, it's the value proposition. It summarizes that online VI curve monitoring provides early, non-intrusive diagnosis and shifts maintenance from reactive to predictive. And then target applications is reiterate the high impact areas, EV, HEV, powertrains, solar inverters, and industrial drives. Third is next step and roadmap. It outlines future research expanding on the data set with more failure types, which initiates field development pilot programs and develops automatic fault classification using advanced AI systems. And this is the practical implementation and integration of the online VI curve monitoring system. Firstly, the non-intrusive monitoring unit. This system is designed for easy retrofitting, utilizing isolated measurement circuits such as current shuts and isolated voltage sensing that connects the power module without altering its primary function. To ensure that the monitoring process is not intrusive, thus it's called non-intrusive monitoring unit. The second is scalable data architecture. This is the data acquired from the monitoring units is packaged and transmitted using industrial protocols like MQTT and Modbus to a central server or cloud logging platform. This architecture allows a single system to efficiently manage data from hundreds of devices across a facility or fleet. Remote access and alerts. This is the process data that is then available for visualization via a secure interface, and most critically, the classification results trigger instant remote alerts via email, SMS, or mobile app to maintenance teams, enabling immediate target intervention. So this is the end of our presentation on the paper that was provided that we looked up. This is again our paper. And to summarize, this is all from us. Thank you for listening to our presentation.